Unveiling Human Origins. Ancient Ape's Ear reveals three-step evolution to bipedalism. 6-million-year-old ape's ear suggests human bipedalism evolved in 3 stages. Transitioning from a 4-limbed scramble to a 2-legged amble distinguishes humans and their ancestors from great apes. However, evidence of this evolutionary shift is scant, making it challenging to understand how our anatomy and mechanics evolved. A recent study of an ancient ape's inner ear proposes that human bipedalism developed through a 3-part process, bridging the gap between arboreal swinging and terrestrial walking. A recent study of an ancient ape's inner ear proposes that human bipedalism developed through a 3-part process, bridging the gap between arboreal swinging and terrestrial walking. This new evidence stems from the skulls of Lufengpithecus, an ape that inhabited East Asia approximately 6 million years ago. Certain dental features of Lufengpithecus suggest it may be a primitive ancestor of modern-day orangutans, known for their arboreal lifestyle. However, other skull analyses place Lufengpithecus closer to African apes, like gorillas and chimpanzees, which primarily exhibit knuckle-walking behavior. This intermediate status makes Lufengpithecus a compelling subject for study, particularly in light of the fragmented fossil record hindering the reconstruction of early human locomotion. In their recent study, Yinan Zhang, a doctoral student in paleontology at the Chinese Academy of Sciences, and colleagues examined the inner ear of Lufengpithecus. While unconventional, the inner ear provides valuable insights into the locomotion of long-extinct creatures. Since 1994, scientists have recognized the vestibular system of the inner ear as a key to understanding the movement of early humans and their relatives. Dutch anatomist Fred Spoor and colleagues pioneered this approach by scanning the inner ear bones of over 150 living and extinct primates. The vestibular system, with its 3 looping semicircular canals, conveys information to the brain about an animal's position and motion in space. Fluid-filled canals and fine hairs sense movement, aiding in balance. The size and shape of the semicircular canals correlate with how mammals, including apes and humans, move around their environment, explains Zhang, the study's lead author. Zhang and the team digitally scanned 3 Lufengpithecus fossils excavated in southern China during the 1970s and 1980s, focusing on the preserved bony labyrinths of the inner ear when other skull parts were damaged. The bony labyrinth comprises 3 semicircular canals, a spiral-shaped cochlea, and a central vestibule. Using modern imaging technologies, we visualized the internal structure of fossil skulls and studied the anatomical details of the semicircular canals to uncover how extinct mammals moved, says Zhang. By comparing the size and shape of Lufengpithecus's inner ear with those of extinct and extant apes, including humans, and early human ancestors like Australopithecus, the researchers reconstructed a clearer picture of early human locomotion. Our study suggests a 3-step evolution of human bipedalism, explains Terry Harrison, senior author of the study and anthropologist at New York University. Prior to Lufengpithecus, the earliest apes moved between branches using only their arms, akin to modern gibbons. Subsequently, Lufengpithecus emerged, exhibiting an intermediary form of locomotion, climbing, clambering, swinging through trees, and moving on 4 limbs on the ground while using 2 limbs to grasp branches. The analysis indicates that Lufengpithecus closely resembled the last common ancestor of apes and humans in its locomotion, providing the foundation from which human bipedalism evolved. This conclusion aligns with previous findings suggesting a gradual emergence of bipedalism, with ancestors stabilizing themselves on trees and branches before fully transitioning to terrestrial walking. Although humans developed bipedalism during their evolutionary history, we originated from a group of highly unique primates that evolved distinct locomotive patterns, Harrison remarks to Laura Basis at Popular Science. Therefore, we are indeed an anomaly.